Hello, everybody, and welcome to the first lecture of Calculus 1 in the summer session 2. So for this lecture, I hope that it will be somewhat enjoyable and interesting and enlightening as to what calculus is all about. But certainly don't feel stressed about this lecture. This is going to be sort of a fun lecture, and it's some of the stuff I talk. It's really going to be a preview of what we're going to be talking about throughout the year. So don't feel like you need to know everything that's going on in this lecture. If you were to fully understand everything that goes on in this lecture, you wouldn't need to take the class anymore. I'm going to well, that might be an exaggeration, but I'm going to be outlining a lot of the stuff that's going on and not fully, this is going to be sort of an overview, and the questions are going to be just making sure that you paid attention and tried to follow the lecture. It's not going to be, there aren't going to be comprehensive, you're not going to need to comprehensively, perfectly understand every concept that I touch on in this lecture. That might be more the case in future lectures, but in this lecture, not so much. This is more of an overview. So I'm going to try to answer for you the question of what questions does calculus answer. It's a good thing to know when you're taking a class is what questions does this class answer. And so we'll dwell on that a bit before we dive into the specifics of the class. We'll dwell on it in this lecture, that is. So, to put it in very general terms, calculus, the question that calculus answers is, if you could put it into one, well, it would be hard to formulate an exact, this is the question, calculus is the answer. But in general terms, it's about the relationship between that which is curved and that which is straight. Now it seems kind of like, well, why do we care? Why do we want to straighten out curves? Why not just let them be curved? And the reasoning for that can be seen by thinking of basic quantities that we rely on for making sense of things like measuring the length of something. So the measurement, length, if you think about it, is sort of an intrinsically straight concept. Now, of course, you can take a tape measure, a flexible tape measure, and you can wrap it around a curved shape. You can say, well, how long is this shape? And then but in order to make the markings on the tape measure has to be straightened out. So that's sort of a workaround. You can say, well, why don't we need calculus? Why do we need calculus? We already have tape measures. But then consider something else. What if you wanted to measure the area of a curved shape? Well, now there isn't really any analog of a tape measure. So thus we need calculus. And then of course your answer could be, well, but what if we just put a whole bunch of triangles in here, measure the area by approximately putting some more straightened out object whose area we know how to measure. Now, if you did that, you would already be starting to get at the ideas of calculus. So that would be the correct train of thought, correct in the sense of leading to calculus. I mean, maybe there's other fruitful thoughts that one could have by contemplating the question of that area, but calculus follows that train of thought. So the history of calculus. So you can imagine that these are not just questions that I'm making up. These are questions that people have naturally, to some extent, more or less, concerned themselves with for a long time, especially with certain curved shapes like a circle And we all learn in school that a circle has that the ratio of the perimeter of a circle to its diameter is perimeter over diameter is pi, and that pi is 3.14 something. I don't actually know the next digit, but this is just something that we're told. But in this class, actually probably more properly in Calculus 2, you will actually learn how to compute this quantity. So for example, I personally don't know what the next digit is, but I could sit down with a piece of paper and pencil because I've taken Calculus 2. I could sit down with a piece of paper and pencil, and I could compute it with arbitrary accuracy. I could get any number of digits. And so that's one of the types of things that we're going to be building up to. Now, a question this simple about the relationship between the curved and the straight was already somewhat satisfactorily studied by Archimedes. So Archimedes is a big name as a precursor to calculus, and he was in his dates 287 to 212 BC. And of course, I'm just going to list a couple names here because it's a hugely complex historical subject to look at, what's really a precursor to calculus, who really contributed original ideas towards the development of calculus. So, of course, I'm just going to list a few names, and maybe I'm going to be unfair and not include everyone who should be included, but I'm going to include the people who stuck out to me as, in the advancements that stuck out to me as most important. Of course, there are also other advancements that I'm sure there could very easily be other advancements that history is unaware of, or that I'm unaware of that some historians know of, and probably others that have not been discovered, probably others that will never be discovered because the record has been destroyed. I would not doubt it. But I'm just going to list a few names. So Archimedes, of course, a big one. He touched on a lot of the concepts that we'll get in this class in a very light way. We began to touch on them. Like another concept that'll come back up is, which will be more the subject of this class, is tangent lines. And he was able to compute, tangent lines to a spiral, whereas before him, people only really knew about tangent lines to circles. His name comes up often as one of the big precursors to calculus. Now, the next name that really struck me from my looking into this just a little bit on Wikipedia and flipping through some books in the library, the next name that struck me as important is Madhava of Sangamagrama. And this is much later, so that says something about how long it took for more recorded progress on this subject. His dates were 1340 to 1425. And Madhava answered, among other things, a slightly more advanced question than just the area of a circle, which is the relationship between the slope of the hypotenuse of a right triangle to the angle. And what he developed is actually sort of an enigma in the history of calculus. In the older history of calculus, if you pick up a book on the history of calculus from a couple hundred years ago, they'll just talk about Newton and Leibniz and some Fubini and some people in Europe that came later, but Madhava was a few hundred years before any of those guys, like 300 years before any of those guys, and he 200 or 300 years, and he didn't lay out all the concepts that are now considered foundational that we are going to be covering in this class, for example, but he's sort of, you could almost say, skipped to some more advanced concepts that you'll learn about in Calculus 2. And he used something called power series that you'll learn about in Calculus 2 that no one touched on for hundreds of years, like I said, after him, but no one in Europe. But what he was able to do was to describe the relationship between the slope and the angle, and what the angle is given a certain slope. So the slope, recall, is the rise over the run. So this is the base, this is the height. So the height is the rise and the base is the run. The slope equals height. Slope equals height over base. And the angle is the length along a circle here. You could say, if you divide the circle into 360 degrees, for example. And so for a concrete example that we all probably are familiar with, or could, would be, if we thought about it for a second, is a triangle where the base is equal to the height. Then this slope right here is 1, and the angle is 45 degrees. If you think about it, because this would be 90 degrees, right? If we made this line right here, we would have 90 degrees, and then this is half of that, so it's 45 degrees. Now here, so here it's, slope 1 corresponds to 45 degrees, so what's the problem? I mean, that's easy. But what Madhava was able to describe is if this is any angle, which, if you took trigonometry, there are a couple other special slopes that that we can say, oh, well, that's the angle corresponding to that is such and such, like, the square root of 3. If the slope is the square root of 3, then the angle is going to be 60 degrees or 30 degrees, and then the other one's 1 over the square root of 3. But in trigonometry, other than typing into your calculator, you certainly didn't learn how to do it if it's an arbitrary angle. Like, say that it was 46 degrees. Well, then what would you do? You type it into your calculator. Or, if calculators didn't exist, you would have to ask Madhava or consult a text from Madhava, or probably Newton. But if you were before Newton, you would need to consult the text from Madhava. So, so if you look at Wikipedia, they will qualify as, well, Madhava didn't lay out the abstract concepts of differentiation and integration. So it's true that he didn't develop the abstract approach to calculus that we're going to be learning in that standard, nowadays. But he did, was able to achieve a lot of things that are like, nowadays we build on top of a whole bunch of abstract framework, and he was able to arrive at them in his own fashion, which is very interesting. But then, of course, the next big name is Newton. And Newton states, actually there are some big names in between too, but the next one I'm going to list is, right before Newton and a little while before Newton, there were things already getting going in terms of measuring areas, like I said, of curved shapes, and some stuff with rates of change. But Newton's the one who really is, he's the one who really, Newton and Leibniz both are really attributed with, but I'm going to talk more about Newton, are really attributed with the modern way of thinking about calculus. Leibniz is more responsible for our notation, and of course there's was a hot battle between Newton and Leibniz about who really founded calculus, because they were contemporaries. Newton didn't publish his work initially, and he claimed that Leibniz had plagiarized it, that he had seen someone publish notes and had plagiarized it and then took credit. So that's a controversy. Fortunately, we won't be dealing with historical controversies much in this class, because math is fairly cut and dried. There's not so much ambiguity when we get into the real meat of the class. But so there's some ambiguity in the history. But so Newton, in Principia Mathematica, and I'm going to link at some point the section 1 of chapter 1 of that book, because it's interesting. In taking this class, it's interesting. It's, maybe I'll have an extra credit assignment or even some questions relating to that section, because it's just really interesting when taking this class in the modern presentation with the book, like the one that we have, to compare that with the original form that this appeared in, which was much more clearly geometrically motivated. Is sort of like Euclid's Elements, if you ever looked at that book. A lot of diagrams and a lot of lengthy descriptions of things, instead of, he doesn't use any variables. There's no x equals this or anything like that. It's just a bunch of geometric diagrams. It's pretty cool. He developed the rest of the concepts that I'm going to talk about in this brief introduction, and indeed that we're going to study in this class. Okay, so now, naming the big names, let's get into some of the problems that are actually, some of the questions that we're answering, as I promised. So, okay, so let's talk about speed. So, speed, how do you define speed? Well, it's the distance traveled. Divided by the travel time. So 60 miles per hour. 60 miles per hour would mean that you go 60 miles, that you will have gone 60 miles. You will go 60 miles when you drive for 1 hour. Now, of course, if you drive for an hour, maybe you have the cruise control on, but if you don't have the cruise control on, even if you do, it's not going to be perfectly 60 miles an hour. Your speed's going to be varying, and you could have stoplights, you could have all sorts of reasons to not have the cruise control on. So your speed's going to be varying. So, well, how do you measure this if you're not actually going 60 miles? You've traveled 60 miles in an hour, but you've been speeding up, slowing down the whole time. How do you give a more precise measurement of how fast you're going at a certain, like your speedometer? Ultimately, your speedometer, the concept of your speedometer is based on concepts of calculus. This is a little bit of a spoiler for what I'm going to say in the next minute or so, but that's where we're going. But if we're going to take more precise measurement, and maybe you're not even going to drive for an hour, but we want to put it in we want to be able to say something about the speed, so we need to change our units to smaller units. So let's replace hours with minutes, and 60 minutes an hour. So we can immediately change this to 1 mile per minute. So now we only need to go 1 mile to have the measurement, but of course you're not going to be, you're not going to be going exactly the same speed for a whole mile even necessarily. So this is, of course, so 60 miles per hour equals 1 mile per minute, right? We just divided both sides by 60. And but now we want a more precise measurement than that. So we'll replace miles with feet. 5,280 feet and then we'll do seconds for 60 seconds. And if you divide those things through, you get 88 feet per second. That's just 5,280 divided by 60 is 88. If I did that division correctly and I scribbled it down earlier, I'm pretty sure I did. But so now that's good. Now you only need to see how many feet have you gone in 1 second. So you're already getting a good measurement of what should be on your speedometer. And of course, you can answer this by looking at how many times your wheels have turned, right? So that's the measurement is how it's sort of behind the scenes. So that is what your speedometer will do, is just, that's how you would define what is going to be on your speedometer is, how far do you go in a second, and then you can change your units back to miles per hour. So there you go. But even a second, you might not be going the same speed for a second. So Newton uses this language of diminishing ad infinitum. So you diminish your units ad infinitum. So the first thing you'd want to do is replace feet with inches and keep going to something infinitely small. So you can say, what's your instantaneous velocity? So if you think about it, the idea that you're speeding up and you're slowing down and you're continuously accelerating and slowing down is not something you can really touch on with your classical algebraic concepts of distance traveled over travel time. You need some more sophisticated concept to get to the instantaneous concept, and that will involve this diminishing ad infinitum that Newton talks about. So that's one form of the problem, and so another form of the problem that I'll mention that at first might not be clear that it's a related problem or an instance of the same problem is, but it, certainly as you take this class it'll become clear, this instance of a problem that we'll be studying over and over in this class, and of the same problem, this instantaneous rate of change. So that is, if you have a square, then you have the length of the square, length and height are going to be the same, and the area is L squared, appropriately named, which is L times L, base times height, L times L. Okay, so what if we increase the area of this square by 1, or the length of the square by 1? How does the area change as the length changes? In 1 what? Well, 1 foot or 1 inch, 1 whatever you want. Then we have a new square that has length L plus 1, and this box here has area L, this one has area L, this one has area 1, so the area of the new square is L squared plus 2L plus 1, which of course is a classic, FOIL method, easy elementary algebra. But so the change in the area of the square, the change in area is 2L plus 1. So you have an area of a square of area L squared, and then you expand the length to 1, and you have a new square with area L squared plus 2L plus 1. It seems like, well, that's just algebra, you change it by 1. Okay, but what if this were continuously growing in time? You could think of it as a growing square that's growing in time. So what if it was a change that was much smaller than 1? Say h, some small h. Well, then the area of this box is going to be LH. The area of this box is going to be h squared, and the area of this box is also going to be LH. So then the change in area is going to be 2LH plus h squared. And if we wanted to see how it's changing continuously, what's the rate of change as the square grows? As it grows by an amount of h, how fast is the area growing as the length is growing? So how fast is the area growing as the length is growing? So there's a statement in words that we can put into a mathematical formula. Is the change in area over the change in length. Change in length. And okay, so the change in area is 2LH plus h squared. And the change in length is h. And that's easy division to carry out. It's just going to be 2L plus h. So now, recall, well, what's h? H is being diminished ad infinitum, to put it into Newton's words. So h, as it's diminished ad infinitum about the instantaneous growth of the square, is just going to disappear. And we're just left with 2L. So that's interesting. So the square is growing at a speed, at a rate of twice the length. So you can think of these two sides, these lengths are growing outwards. It's 2 times the length. You can think of it as these expanding outward. And of course, we'll get more into this as the class goes on, that's for sure. And you can think of a similar thing with the area of a cube. A cube has, as the length of a cube increases, you have 3 square faces, and so it grows. If this were a cube and the 3 square faces were growing out, it would be 3L squared. Of course, I haven't explained that all rigorously. We'll get there. We'll get there. We'll get there, and we'll get much further too. As this class goes on, in our 5 weeks together. So that's one application to keep in mind or one version of this thought that keeps coming up. These questions that calculus answers, and another one is another way of formulating this is in a more abstract form, which is what we'll be focused on more in this class. We'll need to translate between these different versions of the question, but to a large extent, we'll be doing things in this abstract form of graphing Cartesian coordinates, and which were elaborated and historically named after René Descartes, whose dates I unfortunately forgot to write down in my notes. So if you're interested, you can look him up. And there was another Frenchman, actually, and he was sometime in the early Enlightenment, I believe. But there was another Frenchman in the late Middle Ages who actually might more properly be attributed with this idea of Cartesian coordinates, but we still call them Cartesian coordinates. And I unfortunately didn't write down that gentleman's name either, but of course you can look it up. If you look up Cartesian coordinates on Wikipedia, I think you go to the history section, it'll talk about it. The idea of Cartesian coordinates, of course, you have, say, straight lines. So you have a y-axis and an x-axis, and you graph points with coordinates. So like this point, say its height here is 3, and its height here is I'll say it's right. It's back a little bit from 3. So say this is 2.8. And some jargon you might remember from high school, which is pretty irrelevant. I actually just relearned it recently. when preparing for this course, some jargon is, this coordinate's called the abscissa, and this one's called the ordinate. Pretty irrelevant, but sometimes it's fun to know fancy words. Some people don't care for fancy words. Anyways, that's the abscissa, that's the ordinate. But then in Cartesian coordinates, you could represent this point as 2.8 and 3. So beyond the relationship between curved and straight, you can see how our mathematical endeavor, to a large extent, is based on straight line quantities. So this is interesting because it lets us talk about area in terms of straight lines. This straight line and this straight line represent this point. So everything is really broke down into straight lines, and that's really what calculus and the algebra and trigonometry that you learn that lead up to it is all bringing things closer and closer to straight lines, because straight lines are easy to elaborate these abstract concepts about, and then do all these calculations that underlies all the calculations that we use in the quantitative sciences in general. But okay, so Cartesian coordinates. So we can represent these functions that we've talked about before. So we talked about distance traveled as a function of time traveled. We talked about the area of a square as a function of the length of a square. And we could graph any of these quantities here. So for example, we could rename this x-axis, we could rename it to be the time axis, and we could rename the y-axis to be the distance axis. And then we could graph the distance as a function of the time. So the time would be going along this axis, and the distance would be going along this axis. Or the area of a square. This could be the length axis, and this could be the area axis, which of course is now a totally different representation of the problem. But so here's an example here. Like we could have the square of length 1 has area 1. Square of length 2 has area 4. Oh, that's not 4, that's 2. Has area 4. And the square of length 3 has area 9. It's going to be way up here. And if we fill this out, we get the parabola. Of course, we can continue the parabola on the other side too. It's familiar from algebra. And it turns out, and you can think about it if you want. It would be really helpful in being prepared for what's going to come at you later on in this course to think about it. But of course, we'll get more rigorously into it. But I encourage thinking about it, that the instantaneous change in the area that we developed last time is the same as the slope of the tangent line, the line that touches this curve. Of course, don't think that you need to understand why that's the case. It's going to be a big part of what we're getting into later on this week or maybe next week, before too long, as we develop the tools of calculus. But yeah, so that is so the slope of this line is the same as the instantaneous rate of change of the area of a square at the time when the length is equal to this ordinate, and the area is equal, this abscissa, and the area is equal to the ordinate. Or if it was here, it would be the slope of this line. If the length was this quantity, 1.4 or so, or say this is the square root of 2, and this area is 2. So this would be the instantaneous rate of change. So don't think that you needed to fully understand that, but one thing that hopefully that gave you a refresher on, or maybe you already were perfectly good on it, but is this concept of representing functions. That's something that I'll have a question on that in the lecture questions, because that's a key idea, an easy one to think. I just want to get into the meat of the class. I want to do my homework. I don't want to bother thinking about what a function is. I know what a function is. Everyone knows what a function is. But then it's easy to forget what it is without really revisiting the concept sometimes. I'm sure, maybe you're perfectly comfortable with the function, but it never hurts to stop and think about the sort of the concepts and the words that get thrown around constantly, because it's easy to just start doing stuff and say, wait a second, what am I doing? And just, it becomes like muscle memory, even though it's, sort of conceptual. The fundamental theorem of calculus, as it's called, the thing that we're going to be building up to, the crown jewel of Calculus 1, relates the idea of areas of certain curved shapes to rates of change. And so I'm just going to give a brief illustration or attempt to illustrate this with a curvilinear quadrilateral, as Newton might call it. So the area of this. So the way that Newton addressed this, which we'll see later on in this class, we'll revisit this in the last week or two, is to fill in these rectangles. So you have some upper rectangles, or the lower rectangles. These are all below the curve. And then some upper rectangles are all above the curve. And then they can be, to put it in Newton's words, the lengths of the rectangles are diminished ad infinitum, and the number of rectangles is multiplied ad infinitum. So we fill in more rectangles, it'd be skinnier, and there'd be a greater number of them, and that would approximate the area. So that's the idea of integration, which we'll get to more towards the end of the class. But okay, so now say we have the area, so the instantaneous, so say now that this curvilinear quadrilateral is constructed by taking a curve that initially keeps going. Put it in dotted lines. So say we have a curvilinear triangle, this is called. So we have these two straight lines, and then a curved, right angle, and a curved hypotenuse, I guess. So then you could ask, as you move this line along, the line of the furthest, the far right edge of the curvilinear quadrilateral, how is the area, which we'll refer to as the area under the curve later on, but the area within this curvilinear quadrilateral, how is it changing as the right boundary gets moved along? So what's the rate of change of the area with respect to the change of the length? So let's again, call this H, and then call this H, I guess, could be height, but we're using H as a small parameter. So let's call this, L. So say L is the height of the curve. And we could of course, if we're going to do Cartesian coordinates, we could call this curve y equals f of x, and then this would be the point x, and this would be f of x. We'll get to that towards the end of the course. But this height right here, L, is in fact the rate of change of this area. And so this procedure of taking the area under the curve, the area of this curvilinear quadrilateral, is the opposite of the procedure of taking the rate of change of a function. And sort of a weird concept. It's the crown jewel of this class, so of course it's fine if you don't understand it now, because I mean, if you, like I said, like if you fully understood it now, you wouldn't necessarily need to take this class. But rate of change is the opposite of area under the curve. Yeah, and of course this area could be represented as a graph of its own, but that would, be an exercise that we'll get to later. And then this would be the tangent to that curve. But yeah, so that's the fundamental, that's some attempt to explain where we're going with this class ultimately, which is to the fundamental theorem of calculus. So that is it for the first part of the first lecture, and there will be questions attached, and yeah, I look forward to continuing on with you, and enjoy the rest of your day.